So we're going to start off with the introduction real quick. My name is Jamarty Perkins. You can call me JoJo. I am I go to UW, currently a junior, pursuing a physics degree.
Hello, everybody. I'm Matthew Marriott. I'm also a physics major, also minoring in computer science, and glad you're here.
Hi, I'm Alan Sui. I'm an electrical engineer, also pursuing a minor in computer science and software engineering.
Hi, I am Derek Wong. I am currently in the physics major and enrolled in UW.
And hello, I am Lucia. I am currently a sophomore, and my intended major is physics.
Awesome. And so to get a little intro overview, our OPSPARC technology spinoff is basically based on the electric speckle pattern interferometer that was used to test the non-optical surface of the James Webb Telescope, technically like the backplane of the telescope. We're using this technology to find deformations in the hydrogen fuel cells before like certain hazards come into play, technically like hydrogen embrittlement, leakage, and possible corrosions. And so we want to look at basically more efficient, like hydrogen fuel H2 storage in vehicles, because efficient vehicles are in demand. And so in front of us is a 3D model of a car, and if you look closely under it is the storage of the fuel tank, where the fuel tank is basically located either in the trunk of the car or technically under it. And if you move to the left, follow the signs that says this way, we're looking at the motivation, environment, and sustainability. These graphs technically just demonstrate global warming and climate change. Like the third graph technically talks about the annual average temperature in 48 states and high demand for energy. If we continue to the right, going to motivation, technology, evolution, I'm going to hand it off to Matt to talk more about that.
Hello, everybody. So yeah, I'll talk a little bit about hydrogen and hydrogen storage. So we focused on the automotive industry as a case study for hydrogen storage and fuel cells. But again, this type of speckle interferometry can be used for basically any storage tank, for example, methane or oxygen. So we wanted to look into hydrogen specifically due to the fact that there is a challenge of both hydrogen embrittlement for certain tanks like high-strength steels, titanium alloys, and aluminum alloys. But there's also opportunities for improvement in automobile applications for storing enough hydrogen in order to achieve, greater than 300-mile range within your constraints of weight, volume, durability, efficiency, and cost. And cost is sort of the impediment right now. So current tanks in this regime are compressed hydrogen carbon fiber composites, and typically you'll see 350 and 700 bar. Again, costs right now are too high, so that's a big worry. We also have a worry with leaks. So, as you guys know, hydrogen is extremely small. It can leak through tiny pores in welded seams. So one idea for this might be hydrogen detection tape or the IntelliPigment tape. This is just a side idea, but it has a proven track record with space shuttle launches. And hydrogen is a colorless, odorless gas and highly combustible. So it's critically important that we have measures in place to ensure safety. Hydrogen burns in air at a wide range of concentrations from 4 to 75% by volume, and it's also hard to see these flames. We think speckle interferometry could be a viable test technique to detect early signs of material defects in storage tanks that lead to critical failures. This would help facilitate proper standards for hydrogen storage and ensure safety and public acceptance in the broader consumer market for hydrogen fuel cell vehicles. Currently, we just have only 3 vehicles on the market, one from Toyota, one from Hyundai, one from Honda. And the majority of the market share for hydrogen refueling is in California, with 20 out of the 23 refueling stations being there. And also some information about the U.S. hydrogen supply, 95% comes from natural gas reformation process. So yeah, and then basically the major concern as far as hydrogen storage goes is the manufacturing process from different automotive companies and the ease of access to those tanks to where we can, run the interferometry tests on them in as much of an automated way as possible to reduce cost. So yeah, with that, I will turn it over to Alan.
We will be moving to the right here. Just follow the signs, existing non-destructive testing technologies, ultrasonic detection. Go ahead, Alan.
Okay, so a small overview of non-destructive testing, or NDT. Those are basically methods that allow us to test a specific sample without actually altering it in such a way that it's rendered not useful anymore. One of the ones that we looked at was ultrasonic testing. Ultrasonic testing is basically using high-frequency sound waves to inspect the features of an object. You're sending sound waves into this object, and they'll come back to you either as reflections or transmissions if they make it all the way through the material. And by using these waves that either are reflected back to you or transmitted straight through the material, you can construct an image of the inner workings of the material. Sound waves will normally flow uniformly, or they'll flow through uniformly dense materials, but when they encounter something like a defect, like a crack, they'll bounce back. And using some computational analysis, you can quantify these reflected waves to construct an image, kind of like what you're using with the ultrasound for pregnancy tests. So some of the advantages of ultrasonic testing is that it's sensitive to both surface and subsurface defects, depending on the frequency of sound that you're using to penetrate the material. It's got superior depth penetration compared to other NDT methods, and the pulse echo method in particular requires you to only access one side of the material. You don't need all-around access. Ultrasonic testing is highly accurate in determining the position, size, and shapes of specific defects, and the results are given instantaneously to the operator of the machine. The images can be extremely detailed, and the equipment can be extremely portable, as seen in the image over there, where you can carry it around with you on site. However, all of this comes with some disadvantages. So some of those are the surface needs to actually be accessible for you to inspect it. You have to be able to touch and sort of manipulate it. There's a lot of skill and training required to learn how to use this NDT method, and materials that are rough or irregular in shape and density or small are very difficult to inspect with ultrasonic testing. Coarse grains material in particular are very difficult to detect or inspect because of the low sound transmission and high signal noise, so they don't give you a very detailed image at all. Linear defects, or sort of like cracks that are right in line with where you're inspecting the material, are almost invisible because they don't produce any reflected waves. And reference standards require calibration that you need to have tested the material beforehand and need to understand its properties to be inspected. So composite materials may prove to have some difficulties in inspection. And I'm going to bounce it over to Derek to talk about ESPI.
Hi, so ESPI, or otherwise known as electric spectral pattern interferometry, is an optical technique which enables interferometric measurements of surface displacements. The ESPI uses a expanded laser to illuminate the surface of an object, and the surface is then captured and recorded with a CCD camera, which the camera generates an interference pattern, or otherwise known as speckles. This technique uses phase shifting to find fringe patterns. This reveals displacement of the surface as contour lines of deformation. And phase shifting is basically when you take images of an object or surface and layer them over each other. So some advantages of this technique can be it's non-contact, so you don't really need to you could just set it up and then just leave it as it is. So unless you want to do some fine tuning to it, it can be used in almost any surface and or material. So it's very adaptable to whatever you want to use it on. It's very high, precise, and accurate with its results, and it's really easy to see the area of high stress. This technique can also follow displacements in time due to the fact that it uses multiple sequences of measurements. It is very effective as well. So with this technique, there's also some disadvantages. Some of these disadvantages can be, it's for more precise and accurate results, you're going to have the laser and camera be used prolonged onto the surface or object. The results really depend on the performance of the camera, so if something's wrong with the camera, then the results can be inaccurate. And another disadvantage can be that spurious movements can cause inaccurate results for the camera, so like sudden change in movement or sudden turbulence can cause it to give inaccurate results. And I'll pass it on to Lucia.
Sweet. Before doing that, you can just walk towards the sun right here to the warp, and just walk towards the warp. It'll transport you to the top. So I'll turn it to Lucia. We're going to make our way to the left as Lucia talks. Go ahead.
And so these images here are showing the same laser, but the images were taken at different times. So if you zoom in and you see those pictures down at the right corner, you can see the different pixelations between the two and how that is shown in the pictures with the change in time. And as we keep moving to the left, we start to see our information that we have on the James Webb Telescope and how we used it in our project. And so if we keep moving, we see that we have the backbone and an image of the backbone and how it was assembled. And that the next image shows a more diagram of how the phase shifting speckle pattern works. And keep moving down. And so now we're going to focus on this image of the car and how this uses speckle interferometry to test the fuel cell storage of hydrogen to quickly identify whether there is a leakage. So we intend to have a fuel tank to be in the trunk of the car for easy accessibility. And this is an equation that we have on that shows the phase difference between the reference and the object being before and after.
All right, and so as we make our way to the left, oh sweet, you're all here. We're going through the technological challenges. Thank you, Lucia, for that. So some of our technical challenges here is like the funding is the problem, like from who are we going to get funding from. There's also various ways for ESPI to be set up, as you can see, like which is more efficient and what's more accurate in ways of setting it up in order to detect more, more accurate deformation when testing the hydrogen storage. Also, that leads to assembling a team, like who has the knowledge of understanding ESPI. Do we either train our engineers or grab new engineers? And that goes to, keep going to the left. This is a market analysis for NDT techniques. I just want to overview saying that mainly we want to increase the major use of automobile, but our targeted audience are the ones who are in the major users here too. And in red, the projected NDT market, it has positive growth in 2022, as you can tell. To your left, some more. These are more graphs. I just want to touch base on a couple of these graphs. The battery power versus the energy trade-off. And it's given in an acceleration range graph. And the diagonal lines basically indicate max power desires. So these are just various battery technologies where the battery discharged faster under high power demand. And then if you continue more, the other couple of graphs, you can see the fuel cells, electric vehicles. You can see the fuel cells here have high demands in the future versus like gasolines would. And you can see that huge slope, a decrease in slope. In the x-axis is the years, whereas the y-axis is the percentage of new car sales. And going off to our business plan. So we're trying to map the future and hopefully estimate a stage of about 200,000 for all the equipment for the electric speckle interferometer, also the scientists and engineers within that 2 years. We're also seeking funding through government, grants, NSF. Our targeted audience towards huge industries, technically industrial type manufacturing companies, like Toyota has huge demands for more efficient vehicles, so Toyota would be a great target. Also, if we want to take it out of the U.S., other rocket industries like ESA. We also, and on top of that, we going on to the SWOT analysis. For the strength for this technology, it has a huge step of efficiency. It's really automation and versus a human intuition. So it's basically decreasing labor costs and on top of that, increasing safety of the storage. So it'll catch basically early signs of potential hazards, etc. It also decreases the time of inspection. Some weaknesses it contains on top of that, there's more strengths like quick visual imaging detectors. It's, like we said earlier, it's non-contact, so you don't have to have a physical body there to test the deformation of this hydrogen storage. And like I said, there's multiple ways of constructing ESPI. Weaknesses, though. We're not sure if vibrations from outside resources can miss smaller deformation patterns, which on top of that misses stress corrosion cracking on the storage. And a huge weakness we do have is the removal of the storage tanks. So depending on the manufacturers, like how are we going to remove the storage tank in order for the ESPI to detect any of the deformation. Opportunities, it's an increase of industry in the near future, and it's extended the life of fuel cells, and it's not only just testing hydrogen storage, but there's also other elements like nitrogen storage tanks. And we want also opportunities like limiting human errors. Threats, the market cost of technology, it's pretty high. And on top of that, it's the inability to retain current engineers. So basically, using that money to either train our engineers, educate them, and that leads to new knowledge, comes to new problems, whether it's training our engineers, money to train them, educating them, and the amount of time to educate them. And then I'm going to give it off to Alan for our solution.
Okay, so our initial solution is basically to construct a sort of testing harness to inspect these hydrogen fuel cells. This would allow sort of a more routine process for inspecting them so that it's not too dependent on the shape or the size of the fuel cell. So this gives manufacturers a bit of leeway in how they want to design their fuel cells. We still have the problem of how to get those out of the car, but using automation, we oh, sorry.
Continue.
Okay. Using automation, we can eliminate a lot of the human error that comes from manually setting up these cameras and rotating them around the structure. Afterwards, we're going to try to work on a field deployable version where it's more handheld, similar to the ultrasonic testing devices. This way, we could allow mechanics in normal auto mechanic shops to sort of inspect these hydrogen fuel cells, and this would allow for hydrogen fuel powered cars to be more prevalent in industry if you can now take it to your everyday workshop to get it fixed up.
Sweet. Thank you. Yeah, sorry, our solution wandered off somewhere in there, but you can hear it is fine. This is where we're going to end it. So broad impact, I want to just say like the use of ESPI will help pave the way to a more like advanced and efficient type of technology for the future. We want to really just thank you all for taking the time to come hear our presentation. I know it was a lot of technical problems and still you're here. Especially want to thank Professor for basically being an awesome leader throughout this project and pushed us out of our comfort zone to basically learn something new. I also want to thank Dr. Bowers for being the point of contact and being extremely patient with us. We've really enjoyed this project, and I hope you guys enjoyed our presentation too. And Professor, do you want to say something? Professor would like to say something.
Yes, Dr. Bowers and Scott and Maggie, I'm sorry I haven't met you or talked to you before, and I am calling you by your first name, feeling sort of comfortable. Very glad that you could join us today, and we would like to hear from you what you think about the idea and any word of encouragement so that we as a small community of students and teachers here can pick up a part of the puzzle and work on it towards an end goal. And thanks again so much for all your time. And thanks to Dr. Bowers for giving us the opportunity.
So we're leaving off the floor for questions now.
Maggie and Scott, do you have questions that you would like to ask for the team?
The question was, can you anticipate whether this inspection technique would be something you do on a routine basis, like every time you refuel your car, or is this something you would do on an occasional basis, such as when you would bring the car in for routine maintenance to a garage?
Hi, I'm Alan. We anticipate that this technology would be used mostly for maintenance after a significant accident, like a big impact that could possibly damage the fuel cell. That way we could ensure that the vehicle or the tank itself is still safe to be used for the consumer, and if not, they could get it replaced. We anticipate that the fuel cells themselves should be made durable enough to withstand normal inspected everyday use. That way you don't have to inspect it every time you go to refuel, only whenever you take it for routine maintenance at your local mechanic.
One more comment, quickly.
Go ahead, Scott.
Earlier in your presentation, you pointed out that hydrogen into an alloy matrix can weaken the material. So it seems like you might want to consider that this would be a more routine inspection process than just after an accident or some obvious damage occurred to the car. If the wall cell weaken, I can certainly see the potential for catastrophic damage if you weren't inspecting these things on a regular basis. they thought the sort of differences or similarities were with the JWST interferometry, like where their tie-in was between what was used on the telescope or what they perceived was used on the telescope versus their spin-off.
Hi, Dr. Bowers. That was really hard to hear. I'm sorry. Can you repeat that? But, yeah.
Maggie, will you repeat that, please?
Sure. I was wondering what you thought the differences or similarities were between interferometry done on JWST and how you chose to apply it on your spin-off.
I can paraphrase in case you didn't hear. So Maggie wants to know similarities and differences between how you were using this with your spin-off and the actual interferometry of the JWST. And specifically, the interferometry of the back plane.
Hi, this is Matthew. So yeah, basically two huge similarities between our spin-off idea and what was used on the JWST is it's an inspection process that has a whole field approach, or like, wide angle resolution. Yeah, you can look at the entire system with one inspection.
Mm-hmm.
And then also it's a big plus is the non-contact, and so that's why we kind of focused on the advantages and disadvantages of. Yeah, you could be many meters away and do the inspection.
Oh, yeah.
Which is a big plus from ultrasound, which is currently used to do some of these deformation tests.
Mm-hmm. Were you able to hear that, Dr. Bowers?
Yes, Jamarty, we did hear that response. Hold on just one second. Let me see if there are any other questions from Scott and from Maggie. Jamarty, Scott, and Maggie have just a few final comments for you. And first, let's see if you can hear them directly, because I'd like you to hear it from them if you can. So they're going to they're going to start talking, and then if you'll chat in the chat box if you can hear. If not, then I will paraphrase what they say.
Hi, this is Scott Roebuck again. I think this is a really interesting idea, and I think the best application for vehicles that would have a swappable fuel cell container, sort of like if you had, when you get propane gas for a gas grill. If you brought your car in, every time you fill it up, instead of actually refueling with hydrogen, you just swap out the tank. And that gives the owners of the tanks the opportunity to inspect them offline in their own facility, and then you wouldn't have to worry about the huge cost of such a system for individual auto mechanics and things like that. The owners of the gas tanks would really be the people having to bear the burden of the alignment of the system and maintenance of your system and things like that. And I think they would have the expertise to do inspection, not just this technique, but other techniques as well. So I think it's a really interesting idea and a really novel spin-off concept.
Maggie, would you like to make any comments?
I'm good. I think Scott said everything. I think they did a great job.
Jamarty, any last questions or comments from your team?
No, we don't, but we just want to say thank you so much. This was a really interesting, topic to tackle, but it was a great experience. We've learned a lot, not only about the ESP, but we've learned a lot from each other too, and we tackled a lot of challenges. Do you want to say anything too?
Yeah, this was a great team building exercise, and I really enjoyed working on this with everyone here, and I'd really like to thank Scott and Maggie for coming to take a look at our work. Anyone else?
The professor would like to say.
Yes, again, thank you so much for Scott, Maggie, and Dr. Bowers for being available and encouraging us. And we'd also like to know if there are any way in which our students can continue this effort, pick a small piece of the problem and work at it through any formal program at NASA or even at NIA, we would really appreciate it. As an educational institution, it is very important for us to have the students learn new technologies and work towards the future. And thanks again.
Mm-hmm.
Joe Marty, this is Sharon again, and also representing Maggie and Scott. We just want to thank everybody on your team and Subramanian for all of your time and your effort. It's very clear that you worked collaboratively, you worked as a team, and in your presentation it certainly showed that team collaboration as well. Tori has been recording this, so we'll make that available to you all so that you have this. I would imagine this would be something very impressive to include in portfolios in the work that you're doing too. So one last opportunity. Scott, Maggie, anything else you'd like to say?
No, just sorry again it took us so long to connect.
Even people at NASA have trouble with technology sometimes.
Well, I'm just glad we figured out some way to make this work. So thank you, everybody, on the Pacific side of the United States. So from the Pacific coast to the East Coast, we thank you all. And we will be sending you this recording once Tori has a chance just to condense it and edit it a bit. Thank you, guys. And Maggie, Scott, thank you so much for joining us. We'll connect later. I'll see you hopefully in June.
Definitely.
Thanks. Bye-bye.
All right. Thank you. Bye.